Just a few kilometers beneath our feet, the Earth is holding a colossal furnace. It's this massive reservoir of heat, powerful enough to meet a huge chunk of our energy needs. So the big question is, how are engineers actually tapping into this incredible natural power source? Well, let's dive in.
Okay, so here's what we're going to cover. We'll start with the basics. What is geothermal energy really? Then we'll get into the cool stuff, the different ways engineers harness it. We're talking dry steam, wet steam, and this really clever one called hot, dry rock technology. And finally, we'll look ahead at what's next. The dream of tapping magma and the big challenges that stand in the way. All right, first things first. When we say geothermal, what are we actually talking about? Well, it all boils down to our planet's very own natural heat engine. Basically, it's the heat that's generated and stored way down deep inside the Earth. And this heat comes from two places, really. First, you've got the leftover heat from when the planet was first forming, and second, you have this constant heat being produced by the natural decay of radioactive stuff in the crust. The bottom line is, it's this steady, reliable power source that's always there, right beneath us.
Okay, so let's get into our first method for actually tapping this energy. And this is the OG, the classic. It's the most direct way to do it, the dry steam plant.
What's so great about this method is how simple it is. I mean, nature has pretty much done all the heavy lifting for us. See, in a few very special spots on the planet, there's underground water that gets heated up by magma so much that it turns into pure high-pressure steam. All engineers have to do is drill down and plug into this natural pipeline. It's amazing.
And the process itself, super straightforward. You take that high-pressure steam, pipe it straight from the well right into a turbine. The steam spins the turbine, that turbine turns a generator, and boom, you've got electricity. After that, the steam gets cooled down, turns back into water, and we just pump it right back underground to get heated all over again. It's a really elegant, efficient cycle. The tricky part, though, finding these rare natural steam fields to begin with.
Okay, so that brings up a pretty obvious question, right? What happens when you drill down and find super hot water instead of pure steam, which, by the way, is way more common? Well, this is where we get to meet the real workhorse of the geothermal world. Yeah, this is the situation engineers run into most of the time. They find these big underground reservoirs of water that are under so much pressure they stay liquid, even when they're heated to way over 150 degrees Celsius. So that's the puzzle for the engineers. How do you take this insanely hot, high-pressure water and turn it into power?
And the key to solving that puzzle, the piece of engineering that makes this whole thing work, is something called a flash separator. And the idea behind it is just brilliant. You take that super hot, high-pressure water, and you suddenly shoot it into a tank with much lower pressure. And that instant drop in pressure causes a bunch of the water to immediately flash into steam. It's an awesome bit of physics.
This shows you exactly how it works. You've got this mix of hot water and steam coming up from the ground right into the flash separator. The steam gets separated out and boom, it's sent off to power the turbine, just like we saw with the dry steam plants. Then all that leftover hot water, which is sometimes called brine, just gets pumped right back down into the earth. It's a super smart solution for what you usually find underground.
All right, so we've covered how to use natural steam and natural hot water. But what if you find hot rock with no water at all? Now that is a much bigger engineering challenge, and it leads to a really, really innovative solution.
And that brings us to what's called hot, dry rock technology. I love this one, because this is where things get seriously clever. Instead of just looking for the perfect natural geothermal setup, engineers basically said, hey, what if we just made our own? See, in a lot of places, there's no steam, there's no water, there's just incredibly hot, solid rock. We're talking 2 to 5 kilometers down, you can find rock that's over 300 degrees Celsius. So you've got this massive heat source, but you're missing the one thing you need to carry that heat up to the surface: water. So here's the solution, and it's just ingenious. Engineers create the system themselves. They drill one well, an injection well, and they pump cold water down into that hot fractured rock. That water heats up almost instantly. Then they drill a second well, a production well, to bring all that now superheated water back up to the surface, where it drives a turbine. They are literally building their own geothermal reservoir. How cool is that? So we've seen that we can even engineer our own geothermal systems from scratch. So what's next? Well, let's look at the final frontier, the ultimate goal, and also the very real problems that come along with it. Okay, this is the big one, the most ambitious idea out there, tapping directly into magma chambers. We're talking about molten rock, lava, at temperatures from 600 to over 1300 degrees Celsius.
The amount of energy there is just mind-boggling. But as you can imagine, the technological challenge of trying to drill anywhere near that and pull heat out of that kind of environment it's monumental.
And let's be real, tapping any of these geothermal sources comes with some serious hurdles. I mean, you've got the environmental stuff like noise or dealing with gases like hydrogen sulfide, but then there's this constant battle against the physics and chemistry of the deep earth. That super hot mineral-filled water, it is incredibly corrosive. It'll eat through standard equipment, so engineers are having to invent new metals and materials just to stop things from dissolving. You get this mineral buildup called scaling that can clog up pipes in just a few months, and you get these tiny little bits of rock in the steam that act like a sandblaster, just tearing up the turbine blades. These are the tough, day-to-day problems that demand constant, clever solutions.
So all this leaves us with a pretty powerful thought, doesn't it? We have this clean, reliable, basically limitless source of energy sitting right under our feet. The question isn't, is the energy there? We know it is. The real question is, can our engineering, our ingenuity, rise to meet these challenges to fully unlock all that incredible potential for our future?